In this screencast, I'll show you how to use the heats of combustion to calculate the enthalpy for a reaction. So in order to do so, what we're going to need is for all species to be combustible with O2, and they have to form CO2 and H2O. Here, I'm assuming our species are going to be hydrocarbons. For this particular screencast, we're going to ignore any combustion with sulfur or nitrogen. In order to use the heats of combustion to find this heat of reaction, we take the sum of the heats of combustion at standard state of all of the reactants, and we subtract from that the sum of the heats of combustion at standard state of the products. And what we mean by standard state is that the heats of combustion's reference state is 25 degrees C and 1 atmosphere. One thing that you might know in other ways to figure out the heats of reaction, it's the sum of the products minus the sum of the reactants. I'll show you here why we use the reactants minus the products, and this is going to be a result of Hess's law. So let's start with the following reaction. Here we have liquid methanol that will produce formaldehyde gas and hydrogen gas. And what we're looking for is what is the heat of reaction for this particular reaction. So the first thing we do is we write the combustion reactions for all three species and look up their heats of combustion. First, the combustion of liquid methanol, and if we look that up in a table, we find that the heat of combustion for this is negative 726.6 kilojoules per mole. So we'll have in this column the heats of combustion. The next thing we'll look at is the combustion of formaldehyde. So here, the heat of combustion for formaldehyde is negative 563.46 kilojoules per mole. Finally, we're going to look at the combustion of hydrogen gas. And this has the heat of combustion of negative 285.84 kilojoules per mole. And one of the things that you might notice in all of these combustion reactions is they are measured as if the water as a product is liquid, not gas. So now we need to rearrange our three reactions so that our intermediates cancel out and our products and reactants are on the correct sides. Let's do this starting with reaction 1. Here we're going to write it the way it has been given because we want the methanol to be on the left-hand side or as a reactant. And since we write this in the order it's given, we just write the heat of this particular reaction the same. Now let's look at the second reaction. Here we're combusting the formaldehyde. However, we need the formaldehyde as a product, not as a reactant. So we have to reverse the reaction. And by doing that, we reverse the sign of the heat of the combustion. So note, instead of this being negative 563.46 kilojoules per mole, it's going to be positive 563.46. Since we are reversing the reaction, instead of getting heat out of the reaction, we have to put heat in. And finally, let's look at our third reaction, which is the combustion of hydrogen gas. Again, we need the hydrogen gas to be a product, not the reactant. So we're going to have to reverse the reaction, which means we're going to reverse the sign of our heat of combustion. Therefore, instead of it being negative 285.84 kilojoules per mole, it's going to be positive 285.84 kilojoules per mole. Now, let's add all these up. First, let's check that our intermediates cancel out. So we have a carbon dioxide here, which cancels with here. We have two H2Os here, which cancel these two H2Os. And finally, we have 1.5 oxygen gases here and 1.5 O2 on the right. So when we've canceled everything, we get our original reaction back. Methanol liquid goes to formaldehyde gas plus hydrogen gas. And since we've summed up the reactions, we can also sum up the heats of combustion. So the heat of reaction for methanol forming formaldehyde and hydrogen gas using the heats of combustion add up to be 122.7 kilojoules per mole.